Picture this. You sit down, open your favorite game. You hit play, and instantly this massive, beautiful digital world bursts into life on your screen. But before you even see that very first pixel, a tiny piece of silicon hidden deep inside your computer has already crunched millions of calculations. It's wild to think about, but every single app you open, every game you play, and every AI model you tinker with, they all completely depend on the hidden secrets of this one tiny chip, the CPU.
But here is where things get really fascinating. You could walk into a computer store right now and pick up two different processors. You look at the boxes, and both of them proudly say 4.0 gigahertz. On paper, they look completely identical. Yet, if you take them home and plug them in, one of those chips might completely destroy the other, running twice as fast. How is that even possible? Why do the numbers on the box kind of lie to us? Well, today we are going to crack open the silicon and discover how your computer's brain actually works.
Part 1. The Microscopic Factory.
To really understand this mystery, we first need to shrink way, way down. I want you to imagine peering inside a microscopic, high-speed factory. Because your CPU isn't just a lifeless little block of metal. It's a bustling, incredibly organized city that moves at the speed of light. And to get literally anything done, this city relies on a relentless three-step rhythm: fetch, decode, execute. Picture thousands of tiny workers on a super-fast assembly line. First, they fetch an instruction from the outside world. Next, they decode it. They look at the blueprint and figure out exactly what needs to be done. And finally, they execute it, snapping the digital pieces together to finish the job. And they don't just do this once in a while. They do this billions of times every single second. But here's the detail that changes everything. A modern CPU doesn't just do one thing at a time anymore.
Section 2, Cores versus Threads. You've probably heard these words thrown around a lot, right? But most people have no idea what they actually mean. Imagine you're gaming, but you're also recording your screen, downloading a massive update, and running Spotify in the background. How does this tiny factory not just melt down trying to juggle all that? It all comes down to the workers and their hands. The physical cores are your actual physical workers standing on the assembly line. So an 8-core CPU means you literally have 8 dedicated workers on the floor. Simple enough? But what about threads? Well, threads are the multiple tasks those workers are juggling. Engineers created this brilliant concept called hyperthreading. Instead of a worker using just one hand to do a job, they use both hands. While one hand is waiting for a part to arrive, the other hand is already working on the next task. It's one physical worker seamlessly handling 2 tasks at once without ever stopping to take a breath.
Section 3, the Michelin star kitchen.
Okay, so everything we've seen so far makes the CPU look pretty invincible. But even with 1,000 incredibly fast multitasking workers, there is a massive problem lurking in the shadows. This entire factory will completely grind to a halt if it can't find its raw materials instantly. To really picture this, imagine a Michelin star kitchen right in the middle of a frantic Friday night dinner rush. The head chef is amazing. He's incredibly fast, world-class knife skills. But if he has to walk all the way out of the kitchen, down a long hallway, and into the basement just to grab a single pinch of salt, the whole kitchen just stops. The chef himself is fast, but his retrieval process is agonizingly slow. And believe it or not, this is the exact problem your CPU faces with data every single microsecond.
So how on earth did engineers fix it? They built a strict hierarchy. In our tech kitchen, your RAM is that massive storage pantry down in the basement. It holds a ton of ingredients, but it's just too slow to reach. To solve this, CPUs have what's called cache, specifically L1, L2, and L3 cache. Think of this as the kitchen counter sitting directly in front of our chef. It doesn't hold nearly as much food as the basement pantry, but the ingredients are right there for the taking, mere inches away. And finally, you have the registers. These are the chef's literal hands, actively holding the ingredients being chopped. So the secret to a blazing fast CPU isn't just having a fast worker. It's making absolutely sure that chef never, ever has to stand around waiting for ingredients.
Section 4, the Gigahertz Illusion.
Now, this brings us right back to the big mystery we started with. Remember those two 4.0 gigahertz processors from the store? Most people naturally assume gigahertz equals speed, but it doesn't. 4.0 gigahertz simply means the factory's internal clock ticks 4 billion times a second. And yeah, that sounds incredibly fast. But here's the catch. A tick of the clock tells us absolutely nothing about how much work is actually getting done during that single tick.
Let's look at the true secret ingredient here. IPC, or instructions per clock. An older CPU might complete just one single instruction every time that clock ticks. But a modern, beautifully optimized CPU factory, it can complete 4, 8 or even more instructions in that exact same fraction of a second. It's literally the difference between a worker moving 1 box per second and a worker moving 4 boxes per second. The clock speed is completely identical, but the modern CPU is absolutely crushing the workload simply because it is wildly more efficient with its time.
Section 5. The assembly line.
Now, what happens when this perfectly optimized CPU factory needs to collaborate with the rest of your computer? Because it can't do everything alone, right? It has to talk to the other factories. Think of your computer like an intricate, high-speed supply chain. The CPU is your central logistics hub, and it's constantly feeding raw materials to the massive GPU factory, your graphics card. If you're playing a visually stunning game, the GPU needs millions of instructions to draw the shadows, calculate the lighting, and render the textures. But here is where things get really dangerous. If you pair a slow, older CPU with a massive brand new GPU, you create a brutal bottleneck. The CPU simply cannot pack and send instructions fast enough. So that massive, expensive GPU factory ends up sitting completely idle, twiddling its thumbs, just waiting for parts to arrive.
Section 6. The real world. So let's step out of the microscopic silicon layer and into the real world. How do you actually use this information when you're looking at a wall of tech, trying to make a buying decision? Well, it completely depends on what kind of work your factory is doing. If you're an everyday office worker just browsing the web and using spreadsheets, you don't need a massive warehouse. A CPU with basic cores and threads is perfectly fine for that light multitasking. But what if you're a gamer? Games love fast, immediate reactions. So you want a CPU with high IPC, instructions per clock. You want workers who get a massive amount of work done every single tick. Now, what if you're a creator rendering 4K video or developer running complex AI models? That is serious heavy lifting. For that, you need a massive core count. You need as many physical workers on the factory floor as possible just to brute force your way through that massive workload. You now know exactly how this incredible microscopic factory operates. You know the workers, you understand the kitchen cache, and you finally know the real secret behind those tricky clock speeds. But here's the next big mystery. You've got this amazing central CPU factory, and you've got that massive GPU factory down the road. How do all these radically different pieces of hardware actually talk to each other without crashing into each other millions of times a second? Well, that requires a microscopic superhighway network embedded right into the floor of your computer, and that is exactly what we're going to explore next.